Okay, so good afternoon, everyone, and welcome to the session on energy generation, transmission and storage. My name is Claire Dancer. I'm an associate professor at the Warwick Manufacturing Group, which is at the University of Warwick. And I'm also the co-investigator of the EPSRC UK Metamaterials Network. And I have a particular interest in the manufacturing challenges associated with making metamaterials across quite a wide range of applications. So I'm really pleased to be running this session today, and we've got some really good speakers who are going to talk about different topics within this area, which is quite a broad one. I think as we move towards net zero targets for energy use, as we look so much more at energy issues within manufacturing and within industry generally, the efficiency of energy generation and use gets ever more critical. And when we think about metamaterials and how we might use them in those spaces, there's two ways really that we could both enhance the existing technologies, and we could look at enabling new technologies to be developed in this space. So, for example, we can think about metamaterials which might deliver more efficiency in batteries by designing and tailoring our electrodes so that they're more effective and more efficient. We can look at solar cells which could choose and focus wavelengths of light depending on the conditions. And we could think about wind turbines which are invisible to radar, as we're going to hear a bit about today. So we have got speakers today who are going to talk about their work on applying metamaterials within the field of energy. When we've had their talks, we'll take questions and comments from the audience. We'll have a Q&A session, but do please put your questions in as we go along. If there's anything that's really targeted and specific and urgent, I'll ask it straight after the talk, but otherwise we'll cover things in the Q&A, talk about the general issues around the field, and hopefully talk about some future directions in this area, which I think is a relatively new application space for metamaterials compared to some of the others which have perhaps been the subject of more research in the past. Okay, so without any further ado, we're going to move on to our first speaker. Our first speaker is Doug Jones from QinetiQ, who is Technology and Exploitation Lead, and he's going to talk to us about RF control, the control of RF signatures generated by wind turbines. So take it away, Doug.
Thank you, Claire. Thank you very much for having me on. As I say, my name's Doug Jones, so I'm Technology Exploitation Lead at QinetiQ. I've been with QinetiQ for about 20 years. Also, unfortunately, Greg isn't with us today, the technical lead, so but I will do my best to answer any specific technical questions we get. Today, I'm going to try and talk through signature control technologies and how they can be implemented onto wind turbines. I'll give you a little bit of a background on QinetiQ and who we are, talk about QinetiQ's capability in signature control and how that can relate to wind turbine technology. A summary of what we've achieved with that technology, and then the importance of integration into wind turbines, and then just a quick summary of what we've gone through. Next slide, please. Okay, so a little bit of background on QinetiQ. So QinetiQ was initially the Defence Evaluation Research Agency, so a government agency. It split and formed into DSTL, which is Defence Science Technology Labs, and QinetiQ around, I think it's 2003. So we've been a limited company for quite some time now. We have sort of three focuses across the business: experimentation, innovation, test and evaluation, and research. Very much around the create it, test it, use it scenario. Research, experimentation, and innovation is very much the area that I sit within. We do use that test evaluation capability in training rehearsal. We'll talk a little bit more about the research, experimentation, innovation on the next slide. From a test and evaluation perspective, we've got a number of facilities across the UK. We actually run the long-term partner agreement for the UK MOD, which allows us to do lots of testings on air, land and sea ranges, as well as having QinetiQ facilities such as the wind tunnel at Farnborough. We do a lot of testing on commercial airlines. And then training and rehearsal. So we utilise those ranges and other things to enable training and rehearsal. And one of the good examples of that is in Enterprise Test Pilot School, where we train pilots down at Boscombe Down. Next slide, please. So the research, experimentation, innovation. So we've got a lot of areas where QinetiQ focuses. We've got quite a large, we very much focus on our people and use the expertise within those. to deliver really good innovation across a number of technical areas. You can see those across there. Today, we're very much focused on the advanced materials and manufacturing, and what we've done within that to enable us to understand the RF physics behind different materials and how we can utilize those properties to reduce the signatures on wind turbines. Next slide, please. Okay, so who are we? So QinetiQ, 6,000 employees. I say very much focused on our people, working in science and engineering. Research, experiments, innovation leads the QinetiQ R&D element. We've got a broad access to IP and know-how, and we looked at creating customer-oriented solutions within the UK for both military and civil markets. And we can operate independently through those markets as well with partners. And what's that relevance to signature reduced wind turbines? Well, we do understand all the issues we have in terms of complete, so we can run through the whole life cycle where we can look to design, develop and test solutions and understand how those solutions will work. Our signature control products are in service in military and civilian assets. And we understand how to integrate these technologies into wind turbines, and we've actually managed to achieve this, and we'll talk about that a bit later on. Next slide. Okay, on to then the QinetiQ's capability in terms of wind turbine technology. So this is just in line with that sort of create it, test it and use it. So from a creation perspective, QinetiQ has got a lot of experience in creating signal control solutions for defence, and it's applied this in the wind turbine, for wind turbines. We use a structural RAM in terms of our chosen method in this case to really control that radar return and signature, so we can control the signature of wind turbines so they have limited impact on radar. How do we know how much impact we're having? QinetiQ's got bespoke radar modelling tools which can model that impact, so we can understand, look at the topography of the land, what the turbines look like, understand the radar that's looking, and can model what a new wind turbine farm would actually look like, and whether that and how much impact that new farm would have on the radar that's in situ. This technology is actually used already in France, and we work alongside the French government, advising them on the impact of where wind farms may be chosen to be built. In combination with that, once they're actually in situ, we've got the capability to use that multi-band pulsed portable radar to understand actually what the return is. And that gives us sort of the complete sort of end-to-end ability within this sort of technology. In addition, we have been advancing our bespoke modelling tool to take into account the signature control, so we can just not just model, I would say, standard wind turbines and understand we can understand the impact then of what if you put signature controls on that, how would that impact the return that you get. And we've utilised all that knowledge and actually created and working with partners in EDF investors, and created the first and largest wind farm in France, which had only been created because of the signature control technology that we could put in place. Next slide, please. So a bit more then about the signature control and wind turbine capability. So as I mentioned before, QinetiQ's derived this from a lot of work that we've done in the military. We use structural radar absorbent material technology, and that's enabled that first wind farm to be built. It wouldn't have been built without the ability to reduce its radar cross-sectional area, and that's enabled that green power to be put in place without impacting the French weather radar. So what sort of benefits does that structural radar absorbent material offer? It can be integrated into most wind turbine designs, achieving structural and environmental requirements, and this is demonstrated in service. And we'll talk a bit more detail about that on the later slide. It gives the wind farm developers the ability to be approved. So if you're want to put a wind farm in a certain location and that has a heavy impact on radar, you may well get it approved if you can reduce the impact on that radar, and that would increase the ability to either have it built in at all, or even that if it is approved to be built, it might allow you to put additional wind turbines in place. And because of those two things, we also believe that will reduce the cost per kilowatt actually installing it. So if you can install more turbines in a location, that allows you to generate more power with your basic infrastructure costs won't be increased. And in addition, for things like offshore, if you're reducing the impact on radar, you could potentially bring it closer to shore, and then that would allow your infrastructure cost again to be less, because you've got less distance to transit from where the location is to shore, and also there's a much likelihood you'll be in shallower water. So it really does help, not just in terms of more to be built and the impact on radar, but it potentially has a good cost impact as well. Next slide, please. So what have we achieved already? So this is just talking around that in-service signature controlled wind farm in France. Is working with EDF and Vestas. We work very closely with Vestas, they contracted into them, and learned a huge amount in terms of developing, integrating our technology into their wind turbine. It was quite a big challenge. We learned a huge amount in doing it, and the key really is around, so you can look at the size of wind turbines, they're pretty big, 250 meters. And putting additional material in that can really have an impact on how they work. So keeping any parasitic weight to a minimum, but designing something in which adds to the structure but also achieves a signature control really allows us to be successful in this case. And talking around in terms of that radar impact, so in France, around 80% of wind farm planning applications are refused due to the fact that they're near the French weather radar. And QinetiQ radar prediction tool is used around that, so you can really look to see what the impact is and understand where they can be put into place. And that technology, as I say, has enabled France's largest wind farm to be built and installed with minimal impact on the local weather radar. There's 35 turbines 22 kilometers away from a Météo France weather radar. And that actual one has generated equivalent power for 120,000 people. And it wouldn't have been possible without QinetiQ's patented technology and established supply chain. Next slide, please. Okay, so integration of signature control. So I talked a little bit about that earlier. It is a very large challenge. The reason we could manage to achieve this from years of doing this already, where we've integrated it into military platforms, and we've used that knowledge into wind turbines. Again, we wouldn't have been able to achieve it without working very closely with Vestas at the time. And we've taken all that learning to achieve this. What does our designs offer? Well, it adds minimal parasitic weight. Because we're looking at the radar absorbent properties as part of the structure, we're not adding very little additional weight. So we mentioned before just the sheer size of these things. Any weight that you add to the outside is quite significant. Even a sort of a thin layer of material will add a significant amount of weight when you look at something that's 250 meters high. And clearly, you know, these things need to be as light as possible while still structurally sound to enable them to work properly. And adding that additional weight is a real challenge to integration into that. Particularly around the signature control of signature. So in sort of your physical fitness of your radar absorbent material at low frequencies has a huge impact on how you can achieve that signature control. And by using the thickness of the actual structure itself as part of that, it allows you to have really good impact, particularly at that low band. Whereas if you want to add something on the outside, where you're adding new materials onto the outside, to achieve really good signature control in the low band, that has to be a certain thickness. And of course, the thicker you are, the more weight you're adding and the more challenge you have to make it structurally sound when you're integrating it into a wind turbine. We also take into account things like lightning strike protection in doing that. So you need to work around that lightning strike, because clearly you want the things to survive in the environment that it's going to be put in. All the materials are environmentally proven. And we also got technology around radar absorbent tile solutions, so you can tile the tower itself as well as integrating into the wind turbine. And SRAM is compatible with manufacturing methods for reducing the nacelles and nose cones. So QinetiQ has built this experience over many years, and the ability to achieve successful integration into technology into wind turbines. Next slide, please. It's just a bit of summary then of what we've gone through today. So QinetiQ signature control wind turbine technology can be integrated into most turbine designs. It will reduce your radar cross-section in both L and S band, as well as in multi-band. And it gives the wind farm developers the ability to be approved in areas where they may not have been approved previously due to the impact on radar, or potentially as well as increase the number of turbines installed. It should reduce the cost per kilowatt of that installation, because some of your costs will be reduced by either increased number of turbines being able to be built in an area, or in terms of offshore being able to bring it closer to shore, and it can achieve all the structural and environmental requirements there. So the technology really is ready for integration into wind turbines. And I think that was my final slide. So thank you very much for your time, and I'll hand you back to Claire.
Thank you very much, Doug. That was a really interesting talk, and fascinating to hear about the wind turbines. I have some questions, but I'm going to save those for the Q&A session at the end, I think, just to make sure I've got some up my sleeve. Other people, if you would like to add questions to the chat, if you think about them as we go through the session, we'll have lots ready for when we come to the end. But in the meantime, I'm going to introduce our second speaker. So our second speaker is Dr. Melissa Riley from TWI, and she's going to talk to us about manufacturing methods for metasurfaces. Melissa is a principal project leader in surface engineering, corrosion and interfaces at TWI, leading the work on coatings of composites. So I'm looking forward to another super interesting talk. Thanks, Melissa.
Brilliant, thank you. So hopefully you can all see my screen. Brilliant. Yep. So thank you for the invitation to speak today. It's really good to follow on from Doug's talk as well. Hear what they've, the other technologies. I'm going to talk today about the work we've been doing at TWI in conjunction with the University of Exeter since, when did we start this work? 2020, losing track of time, on development of manufacturing methods for metasurfaces. So I'm presenting on behalf of the team here at TWI and Exeter, and then also Warwick, who are involved in the subsequent work that we're doing. So a little bit about TWI. TWI is a research technology organisation. Our head office is in Cambridge in the UK, but we've got 4 of the sites in the UK and 11 overseas subsidiaries. We've got basically the company is effectively owned by its members, and there's about 600-700 members around the globe who come to us for advice on joining technologies. And so we've got a very multidisciplinary team working on our traditional technologies that have come from welding, but very much now we're involved in lots of other joining technologies involving composites and coatings and NDT and lots of other technologies. So that's a little bit about TWI. We started working in this area as part of the phase 1 programme for the offshore wind farm development calls that DASA put out. And we were looking at developing a novel method for creating a conductive coating on turbine blades that absorb radar, and we're working with University of Exeter. And this work has come about following a lot of the work we've been doing on coating on composites for many years at TWI. Obviously, I'm not going to go into all the details. There's a lot more expertise on metamaterials in the conference today than my knowledge. But basically, what we're looking to do is, can we produce a metasurface at scale, and can we incorporate it into existing blade technologies as a different process to the work that QinetiQ have been doing, and does it function as intended? So my background is in surface engineering and coating at TWI. We get involved in a lot of work looking at application of different materials, surface modification by different methods. We have a range of coating processes at TWI. My background is in thermal spraying, and we've obviously got a backup in terms of materials characterization and performance evaluation on a wide range of topics. So for those of you who don't know anything about thermal spraying, it basically involves taking a powder or wire consumable and then melting that consumable by combustion or electrical means through an arc or plasma. And those molten or partially molten droplets are propelled onto the substrate, they impact and they solidify to form a coating. So there's a number of different processes that are relevant. The most basic is flame spray technology, which is basically a wire or powder consumable with a single cylinder of oxygen and a fuel gas. And you generally get a reasonable, depending on whether it's powder or wire, will influence the coating quality. But powder-based processes are a lot more porous, and you tend to end up with a microstructure that looks a little bit like this. And that's similar as well to an arc sprayed coating, where you've got two consumable wires, you generate an arc between them, and then compressed air propels those droplets onto the substrate. Plasma spraying, very high temperature process, and you can spray, if you can get the consumable, you can spray virtually any material. And then we have the high velocity oxy-fuel combustion processes that are designed to produce very dense coatings because you're spraying material at supersonic velocities. So that's thermal spraying in a nutshell. Obviously, when you come to being able to coat composites, you have a bit of a challenge in that you have a thermal process combined with a low thermal tolerance substrate. So a lot of the work that I've been involved in historically has been looking at how we actually are able to prepare coatings onto composites, avoid damaging the composite significantly when we prepare the surface for coating. What happens in terms of thermal degradation, abrasion and erosion of spray particles can be a problem, as well as CTE mismatch and residual stresses. So basically, we've got a lot of know-how in terms of how to prepare and deposit coatings onto composites. And we've then got involved in doing a lot of work on applying conductive coatings for EM shielding applications and lightning strike performance. And we've taken this knowledge from a significant amount of work with the aerospace community to then looking at applying these coatings in discrete locations to produce metasurfaces. We know from previous work in the aerospace sector, we can apply things at scale. We've done work looking at the feasibility of applying technologies to aircraft wing sections and fuselage sections. So it seems a natural approach to continue this technology for the metasurfaces. So this is an example of conductive coating on a composite. And we've basically applied these, and then we've modified the coating to produce the metasurface design that University of Exeter have designed to be relevant to wind turbines. And the questions then are, can we produce a functioning metasurface in a metal sprayed coating that provides the right response? So the phase 1 program was basically looking at preparation of substrate materials, coating application, production of the metasurfaces, and then considering what happens in terms of scale up, which is now what we're working on in terms of phase 2. So University of Exeter have come up with a number of designs, and we've been looking at reducing the reflection at the relevant bandwidths. So we've done a lot, they're doing a lot of work looking at different designs to take into consideration the blade geometry and what's applicable from an industrial perspective, and thinking about the commercialization of this technology if it's successful. There's multiple processing routes for creating the metasurfaces. They can be printing or direct deposition techniques. They may involve masking, machining, ablation, or etching. And basically, these all vary in terms of their suitability for manufacturing in terms of CapEx requirements, operating costs, processing speed, the accuracy of the patterning and the resolution, also the geometrical considerations, and also the environmental impact. So some technologies may have negative connotations in terms of reach, for example, and they all vary in terms of the feature sizes that can be produced. So these are some of the things that we've been looking at. We then went on to test our 0.5 meter demonstrator panel at University of Exeter, and we're actually able to show that the experimental results that we got matched reasonably well with the simulation. So this has basically opened up a new processing route for achieving metasurfaces at scale. And I think one of the things to highlight with this project is that we did this in a very rapid time frame. The program was meant to be about 9 months long, and we condensed it into a very short time frame just with the funding requirements. So moving on from that, we have managed to demonstrate a new process that is potentially applicable for wind turbines. And then we're looking at how we can take this forward and upscale the technology. We've secured a second round of funding as part of the phase 2 wind farms program, where we've also engaged with Warwick, the offshore renewable energy catapult, and we're working with them to look at demonstrating these technologies at scale, considering how we integrate those processes into the existing manufacturing processes, and actually doing some performance evaluation alongside all the design work that University of Exeter will doing to look at some of the more detailed requirements. So part of the work is involving using offline programming and simulation of robot toolpaths. We have a large-scale coating facility at TWI that we can use for upscaling and manufacturing development. We also work closely with our composites team as well. And there's the robotics specialists and the coating specialists, etc. And what we're doing is bringing this technology together and looking at applying or developing the procedures that allow us to develop these coatings, look at things like production rates and things for the different processes. So at the moment, we are actually upgrading our facility to install a new track system and a second robot. This actually allows us to do some large-scale coating demonstrators, not obviously as big as a wind turbine, but it's allowing us to look at applying coatings on representative geometries. And we can then look at what we're doing in terms of the various processes that are involved in creating the metasurfaces. We're then able to consider if we want to introduce multiple processes or inspection techniques, what we need to do in terms of production. So we're thinking ahead to if the technologies are successful and we can validate it in it's suitable for particular environments. And we've got a lot of expertise looking at performance of coatings, for example, in offshore wind turbine applications. So there's a lot of know-how within TWI to sort of bring to the party with some of the testing that we need to do alongside the expertise from Warwick. So the targets for this program are to basically come up with further design iterations that allow us to look at improving the efficiency of the process and the design to make it more suitable for large-scale applications, demonstrating that functionality on representative materials and representative geometries. So we're looking at doing some small-scale demonstrators and then also some wind turbine blade sections, and then validating that functionality alongside the experimental models. And then following on from that, the aim is to then look at further improving those designs, looking at some of the integration requirements, the process economics, to basically push the process to the most cost-effective route, and the systems integration requirements that we need alongside the health and safety side of things as well. Obviously, key considerations are the robustness of these technologies in service, performance evaluation in representative test environments, which we're doing some work in phase 2, but I'd anticipate if this work continues, there will be further work, but also compatibility with the lightning strike protection and anti-icing systems. And there's a lot of know-how from the work we've done on the aerospace sector in that space as well. So basically, TWI is in a position to offer the ability to look at an alternative manufacturing route for producing metasurfaces at scale. And I think this is one of the key challenges with some of the technologies to date of how do you take some of these designs that are perhaps produced in the lab and actually apply them in an industrial setting. So what we're looking at is taking these technologies up through the TRL scale, aligned with the technologies and the expertise that we have within the organisation. So that's a bit of a whistle-stop tour of what we're doing. If anybody has any specific areas of interest, then please feel free to touch base with us after the event. You can contact me or my colleague James Smith. So thank you very much.
Thanks, Melissa. That was fascinating. The scale you're working at is quite something. Very different to the scale we work at in my lab, for sure. Okay, so I'm not seeing specific questions so much coming through yet. So I think we'll roll them all up into the Q&A at the end and do lots of questions all together. And we will carry on to our final speaker in the session, who is Dr. Ragip Palla from Meta. And we're going to move away from wind turbines a little bit and talk about solar cell efficiency augmentation with Metamaterials. So I will hand over to you, Ragip, if you're ready.
Hello, everyone. Let me share my screen.
Great.
Thank you for the introduction. Can you see my screen?
We can see it, but it's a little bit small. I think we're seeing your presenter mode.
All right, I see. All right, let me try to reshare the file itself. All right, maybe if I do this, maybe that won't help. Is this better?
I think if you go into presentation mode and then you can select just the screen, that should work. Yeah, so go in there and then in view in the top right hand corner.
If you just change the display settings, the third icon along.
Oh, yeah,
all right, I set up displays, I guess. All right, can you see it now?
Perfect.
Oh, great.
Great.
Okay, you can see my screen, right?
Yes, we can see.
Okay, great. Again, thank you for the introduction and allowing us to present in this conference. In this presentation, I will talk about the design and fabrication of non-structured and metamaterial coatings for next generation solar cells with improved module efficiencies. And I'm Ragip Palla. I'm the director of the Metamaterial Research and Innovation, joining this call from California, Pleasanton. Unfortunately, I'm still at home and I don't have a camera set up in my desktop, so apologies for not being able to join with the camera. I will start with this statement, which basically states that this presentation includes forward-looking statements which involve significant risks and uncertainties that could cause actual results that differ materially. I believe we had other presentations in prior sessions, and our colleagues have made a good introduction to the company itself. I'm not going to go into details of what we're doing, but I will briefly mention about our company. Metamaterials was established in 2011. It's a smart materials and photonics company that is changing the way basically we interact and benefit from light. And the company is publicly traded in US and NASDAQ, and we are based on Dartmouth, California, and we have a global footprint. We have several locations over the world. we have basically I'm joining from the Pleasanton, California, and our headquarters is in Dartmouth, Canada, and we have several locations in Canada with fabrication facilities, as well as a branch in the UK as well. Our activities, we have several different manufacturing capabilities with different target applications, from protection to lithography capabilities for like making basically structures that have wide variety of applications, which I'm going to focus on today. And we have also sensing capabilities such as like medical applications for biosensing. In this talk, I will discuss about combining electrical and optical functionalities in a small form factor, which is one of the big challenges for next generation ultra-thin film solar cells. This challenge is driven by the wavelength of light, which results in the large mismatch between electronic and optical components. So one solution is using nanostructured elements, which allows us to control the light-matter interaction at the sub-wavelength scale. In the past 2 decades, we have seen very beautiful examples which can replicate dielectric and optical functionalities on an ultra-thin film factor. For example, you can see here a nice example is where we can diffract the beam, we can do focusing, and as well as we can do polarization control and light field functionalities. On the other hand, until recently, we could only fabricate such structures using expensive tools such as e-beam lithography. And the challenge still remains to find basically a scalable technique that can enable us low-cost manufacturing. At Meta, we have 2 lithography capabilities to create dielectric and metallic nanostructures at scale. One of them is roll-to-roll non-impinging lithography and rolling mask lithography. With the NIL, we can fabricate roll-to-roll grayscale structures. In this picture here, you can see an AFM image of sub-wavelength nanostructures combined with microstructures. So this gives us a unique advantage that we can basically manipulate the color at various levels and depth. And the separate litho technique with the rolling mask lithography, which is a proprietary technique, we can print any type of dielectric as well as metallic nanostructures at scale. So just to elaborate a little more on the capabilities here, first of all, one of the key ingredients is the design. We design in-house design capability. For each application, we need basically a tailored nanostructure design. In addition to that, we have to incorporate the 9 ideal experimental discrepancies. But here in our facilities, we have in-house e-beam lithography. So we can basically create the masters and the designs that are necessary for each application and do a small scale fabrication and testing. Once basically the design is completed, we transfer this design for replication and recombination into a large area master, which is as large as 1.2 meters in wide. And then the mask is fed into 1.2 meter of, sorry, somehow it got back. So once the master is fabricated, it's fed into 1.2 meter wide web UV cast NIL, which can print really fast, up to 150 meters per minute of these non-structured coatings. And then in the last step, we do a roll-to-roll deposition to basically coat these structures. In terms of the application space, one of the products that we have currently is we call color optic, which combines the micro and nanostructures to create this depth and color and motion. What we see here in these pictures, actually, we don't use any inks or dyes. These are purely plasmonic elements, so truly metasurface metamaterial elements, and we can tune the structure dimensions, the plasma, basically the height, the diameter, the pitch, and shift the resonant absorption, which defines the security features that we use for RGB colors, and then create these 3-dimensional images, which you only see here, 2-dimensional. And this basically provides us ultra high resolution, which is impossible to reduce using like other methods. So as a different lithography technique to create metamaterial structures at scale, we have a proprietary technique called rolling mask lithography. I'm not going to go into the details of the system itself, but it is quite similar to a standard lithography process, which consists of photoresist coating, an exposure process, where we have the rolling element with a transparent mask, and then we develop and rinse, and then do metallization or dielectric coatings and lift off process. And here, the discrepancy that makes us, allows us to make nanostructured elements is the lithography process itself. We are using phase shift lithography in a roll-to-roll manner, and our masks are transparent here. We are just using actually standard materials, such as the photoresist and the UV eye line. But because of the nanostructured mask, we create an interference pattern right in the photoresist, which is a sub-wavelength. And this way, basically, we can create these nanometer scale structures with low-cost materials and the production scheme. So in terms of the structures, we can create, as I said, dielectric as well as metallic nanostructures. And one of the key elements for next generation, like a high efficiency solar cell, is creating ultra high transparency conductive films. And we created NanoWeb in this regard, which you can see on this chart on the right-hand side, shows the transparency versus sheet resistance. And compared to other existing technologies, such as thin film, like ITO, like conducting oxides, as well as other nanowire technologies, we stand alone in terms of the transparency that we can achieve compared to the sheet resistance. So with this, I will now switch the gears and describe our approach for realizing nanostructured coatings for next generation solar modules in terms of the design space. One of the needs for the mobile applications in particular is creating ultra lightweight solar cells with high efficiencies. And this in particularly for like structures, systems that require flexibility, that you can basically embed these solar modules onto curved surfaces, as well as systems that require ultra lightweight, such as the UAVs and high altitude aircrafts, require maintaining the efficiency while creating this ultra lightweight. And for this, we are developing anti-reflective coatings, as well as light trapping films, which can be placed directly onto modules, as well as developed on the module preparation and then solar cell modulation itself. Our approach consists of actually combining two different levels or structures, I would say. In one case, we create these metamaterials structures which can improve the efficiency compared to existing solutions. So what you see on the left-hand side basically is the cell thickness dependence of the efficiency. As you lower your thickness to create ultra lightweight solar cells, the systems basically degrade in the efficiency. And one way to improve this is using improved optics. However, there are still limitations. And if you use nanostructured materials, you can suppress these limitations and create really ultra high efficiency modules with thin film, lightweight thin film solar cells. And the target area in terms of the module efficiencies are basically, we are looking into watts per square meter per kilogram. So if you look at this chart on the right-hand side, you can see there is a significant gap between traditional solar cells, which are low cost, and the high cost solar cells like multi-junction 3-5 elements. There's a gap here that does not actually have any kind of solution in terms of the efficiency per kilogram. And this is where we want to fill in. Another challenge that is come for the ultra lightweight solar cells is the angular dependence. Like it's in particular for places that have high latitude angles, like in terms of, for instance, in the UK, as well as like various European countries, the sun never comes at perpendicularly onto the solar modules. And what you see on this chart is actually the efficiency throughout the year as a function of incident angles throughout the day. So this is the time of the day, and this is the different days over the year. And you can see overall angles is basically never 0 degrees. In fact, the average angle actually is more than 50 degrees overall. And that becomes actually a major challenge in maintaining the efficiency of the solar cell throughout the day. Another challenge, especially for high altitude systems like UAVs, is the heating up of the modules. So this is showing the efficiency as a function of temperature, and you can see basically a significant degradation. So for next generation solar cells, these two problems has to be handled properly. And in that regard, we came up with this solar heat cell design concept, where we have several elements, including a structured glass, ultra-thin film structured glass that increases the thermal emissivity and improves the solar module efficiency, as well as an AR coating on top, which actually consists of nanometer scale light trapping elements that can enhance the solar module efficiency at oblique angles. And also this highly efficient transparent conductive films, which improve the charge carrier collection efficiency. So just to elaborate more on the coatings for increased transmission at oblique angles, what you see on the left-hand side is the efficiency, the reflectance as a function of angle with different type of coatings. As you can see here, even with a magnesium difluoride, which is low index, which is optimized for high angle, there is a limitation. And that limitation comes from actually a basic concept we call a Brewster condition. So at one polarization at a particular angle at 60 degrees, well, depending on the refractive index, the light is completely reflected. So no matter what you do, if it is a planar film, and there is basically no, I would say, low index film that exists that can prevent this type of reflection loss. And what we do here is basically by optimizing a non-structured film, we can suppress this limit and increase the transmission even at oblique angles. And on the right-hand side, you see the efficiency of the, well, this is actually the charge carrier, the total short circuit current for a 3-5 cell with an optimized coating on the red, and then the planar glass is on the blue color. You can see an increase of 15% to 13% depending on the angle. We have fabricated these structures and applied them onto a solar module to see the efficiency increase. And indeed, we were able to replicate our theoretical predictions, and basically we have achieved a broadband improvement of the photocurrent at oblique angles. On the right-hand side, you can see the performance as a function of angle for various different wavelengths from 400 to 650 nanometers. As a separate approach, I mentioned about improving the thermal emissivity. And for that, by using these metasolar, or well, I would say nanostructured or microstructured elements and combining them, we were able to increase the emissivity of the solar modules. On the right-hand side, what you see is a bare module efficiency at room temperature, which is 28%. So for especially for systems that are operating at high altitudes, because of the heating up, especially for modules that are lightweight, which are coated with plastic films, the emissivity is actually as low as 0.57. And this results in high temperatures that basically degrades the efficiency from 28% to 20%. And by using these coatings, we improve the thermal emissivity, which is the main mechanism for thermal dissipation, and can lower the temperature from 150 degrees roughly to 60 degrees. And this allows us to maintain the efficiency as high as 25%. even operating at a high altitudes. Another approach we are looking actually is using Mi resonators, combining like a small and like a large elements optimized for light trapping using basically Mi resonator structures. We were able to improve the efficiency of ultra thin film solar cells. What you see on the right-hand side summarizes basically the structures that we have tested for planar silicon film, which is in this case only 3 micron thick, which is really ultra thin. The efficiency is actually on the order of, like, in this case, we are just looking at the current density. It is as low as like a 14 milliamps per centimeter square. As we apply these different coatings, including the optimized silicon nitride ARC coating, which is the standard coatings that people use for these solar cells, our coatings, which are these metamaterial elements, can increase the efficiency basically up to 22%, like a 22 milliamps per centimeter square. And this is an 11% efficiency increase compared to the standard ARC coatings. I will skip on this, and with this, I would like to conclude my presentation. So in summary, we have provided mechanisms that we can improve the efficiency by having these ultra lightweight coatings for light trapping at oblique angles, as well as providing a broadband increase in the transmission using Mi resonators. I haven't really get into the depth of charge carrier collection efficiency of using NanoWeb due to the limited time. But this is also in line with our next trials using NanoWeb for improving the solar cell efficiencies for various different platforms. With that, I would like to also invite you to check our websites for I4I Innovation Hub, which we are aiming for. Actually, for this year, the funding call is closed, but I would like to ask all of you to keep an eye on the next call, which is going to happen later this year. With this, I would like to thank you. And if you have any questions, I would be happy to answer as well.
Great, thank you very much, Ragip. And that brings all our speaking sessions to an end, and we are going to have some questions now, and I can see questions flooding in. So we are going to have some things. I think we'll switch back to everybody being on cameras, everyone who's got cameras. So if you could turn your cameras back on, please, speakers, and then when we come to you, we will go round. So I think we've seen quite a large difference in scale here, which is quite interesting across the wind turbines to the solar cells, and I think there's some really interesting food for thought in there immediately. I think my first question, which I'm gonna take my question first because I get to be in the chair and get to ask it, and I'm going to ask everybody, is what's the biggest challenge in manufacturing these kind of metamaterials at the moment, and what might we be able to tackle from a research or from an industry perspective to try and solve some of those challenges? I'll go in order of speakers because it seems fair. So I'll go to Doug first.
That's a good question. I think scale is one of those things that's always a challenge, and able to actually get it to something that's sensible and bring it to something that's affordable. I think that would be where I would look to focus. I think the key is it's very good to come up with a system that that works in the lab and you can guess, oh, that looks really good, and it's, it's great science and everyone loves it. It's that exploitation piece, and how do you grow that and make it affordable and useful. I think that's probably the biggest challenge, I'll say, Ryan.
That's interesting. How do we get through that barrier where you've got a great idea in the lab, but how do you demonstrate enough potential that someone will take it up, like QinetiQ or TWI or Meta? How do we jump over that big big hole?
So yeah, that's the killer question.
Oh, I'm sorry, I promised no killer questions.
That's all right. That's all right. So I think it's a challenge. I think that, and it's something that I think you'll struggle with all materials. One of the things is, I think it's just putting yourself out there a little bit, making sure that people understand what the capability is and what it can achieve. I think there's sometimes a gap between what people who want technology understand can be achieved, and so they're not sometimes asking the right question. So it's that, how do you, I'll say, simplify your messaging to those of us who aren't hugely scientifically gifted, and say, well, actually, this is what it can really achieve in life. And it's that, it's finding that marriage between someone who understands what will be useful and actually they can utilize, versus what technology is available. And so I think it's just making sure that you try and have those conversations and bridge that gap between the very, very technical science and saying, oh, this is great, to someone who actually knows what they need in industry, who might, in the nicest possible way, glaze over when they get completely lost with a lot of scientific terminology. And I think that's that's probably the biggest challenge and the gap that we struggle with, and that's something that we hopefully we do a little bit of, and I think that's the bit that it's just putting it out there and trying to keep it simple and think not just what I've done, but how I can use it and present it in that way, so it can be used for this. It will solve this problem, rather than I found this great scientific thing, which might be great, and you might want to advertise that, but then think around how will it actually be utilised, and try and present it in that way.
That's super interesting. I think that's a really great lesson for all of us academics in the room. And I will just put in a small plug here for the EPSIC Metamaterials Network, which is academics and industrialists all together. So if you haven't signed up for that, please go to metamaterials.network, it's our website, and sign up into our database, because we are trying to do some of that and at least put people in the same room. Okay, I'm going to go around to Melissa and Ragip and see if they want to expand on anything there.
Yeah, I think from my perspective, actually being able to scale up these metasurface designs and ensure that you've got the accuracy that's required, and actually demonstrate the functionality over real life components and geometries is key. And I think what we've found is, not only with the work we're doing at the moment, but other projects of this sort of type, it's bringing together the different expertise from the scientists at the lower TRL, the people in the middle of the TRL manufacturing readiness scale, with the people who actually want to use the technology to really understand what's required and address all the things that need to be addressed before it can actually become a production process. And it's making sure that things are validated at the various stages. And what we found is a lot of back and forth. So that it's getting people in the room and being able to discuss the different aspects is really beneficial, and you know, a lot of fun in a lot of ways, sort of combining the sort of science and the physics with the practicalities of, okay, how do we make this, and what does this result mean? So yeah, and I think one of the things that's always going to be key is, where does the funding come from to actually support the development of these technologies, and that for me, I think, will determine how successful some of them are. And I think it's very much also dependent on what the application is. So that, you know, certain applications may require one technology over another, for example, and it's assessing that.
It's assessing that, isn't it? And it's also sometimes using what you've seen before to reapply it, but sometimes you have to start again and invent something really new. I was interested, Melissa, in when you were talking through your project, you were in 3 different phases. Was that 3 different tranches of money coming through?
Yeah, I mean, hopefully
that must be quite challenging.
We're thinking ahead to, okay, we know what we're doing on phase 2 at the moment, but actually we're also thinking already of things that we need to do for phase 3 to take this forward. So it's this classic scenario of sort of looking at what we've done before, looking at what we're doing now, and looking at what we need to do next to kind of bring it all together. And I think it's one of the things that I sort of recognize that we need to be doing is kind of going, okay, what is the information that we're getting now? What does that mean, and what do we need to do next to address the challenges?
Great, really interesting. Ragip, did you have anything to add? I haven't got a camera for you. So.
Yeah, I would like to say a few words as well.
Yeah, absolutely.
As Meta, actually, we were trying to fill in this gap, as I said earlier in the presentation, like to realize these large-scale manufacturing capabilities for metamaterial and metasurface elements. And the real challenge here is, as like our colleagues mentioned, is more, it's an application-dependent question. For instance, for these coatings, some of the coatings that we have already some products which are metamaterial based or metasurface based, and we can actually fabricate and produce them as large as like a 7 million meters square per year. So we have that type of capability for a particular application. That, I mean, this is a well-known technique, which is NAL, and we are looking into how can we apply this large-scale manufacturing technique for different applications. And we do have some applications, but now we are trying to expand that. But in terms of the question now, what are the limitations, or what are other type of fabrication techniques that we need to make any type of metamaterial elements or metasurface elements? That's a challenging question, because NAL, as you know, is a limited technique in terms of the materials that we can utilize. There are more low index materials, and you cannot just create any type of elements or any type of metasurface or metamaterial structures. I would say in terms of the manufacturing itself, one of the key missing elements is roll-to-roll etching like techniques. Like, for instance, if you have a thin film of a high index material, this could be dielectric or it could be metallic. We can create the roll-to-roll thin films, and we can actually make patterns using roll-to-roll nanoimprint, but we would need a roll-to-roll etching technique to basically, I would say, fill in the gap. So, and at that moment, we can basically create any sort of metamaterial, or, well, not maybe any sort of, I shouldn't say that, because metamaterial concepts are more broader. We can make 3D dimensional structures. But in terms of metasurface elements, which are more on the two-dimensional space, I would say we can create any sort of two-dimensional metasurface elements if we had this capability. I think that's really the missing element in terms of the manufacturing capabilities. And we are actually working towards that as well, to fitting that gap as well, hopefully in a soon future.
Great, I look forward to seeing that. That's a really interesting, yeah, that subtractive technique can be quite powerful, but actually thinking about how it works is challenging me a bit, for sure. Great, thank you very much for those very thought-provoking answers to a very general question. I am going to tackle some of the long list of questions that we now have, because we gave people time to think and they have delivered. So let me work down. So I think the first one is probably more for Doug, possibly slightly for Melissa, but it's about wind turbines from Steve Boxall. Oh, for Doug. How many wind turbines are actually made in the UK as opposed to just being assembled here? I don't know, you may not know the answer to that. And what strategies are in place to ensure we make them and the materials in them in the UK, and not just doing the research, design and consultancy?
So I can't talk to exactly how many wind turbines are made in the UK, but I know when we worked with Vestas, they have a manufacturing plant within the UK. So there are capabilities within the UK, and I think the materials, it probably speaks to what solution they go for in the end, particularly these new materials and where they are. I know we've got a relatively robust supply chain, and some of it does come from the UK, but it is not all from the UK based. So. Yeah, that's probably as much as I can go into the detail on that one.
I think it's always going to be a challenging question, and there's a balancing act here over, do we want to make everything in the UK or do we not? So yes, but fair question. Okay, second question on my list is for Melissa from Carl Limer. Do you anticipate any issues with edge effects from registration mismatch between adjacent etched metasurface patterns as part of the scale-up process? So I think this is thinking about, we're doing tiles of them and then putting them together, or doing it in batches, the spray, and then moving on. So I don't know if you have any thoughts on that.
Yeah, it's one of the things that we're looking at, the accuracy of patterning and what happens when you deal with complex curvatures. So we've got ways and means of trying to assess that as part of our development, because this is one of the key questions. So although there's lots of things that we need to assess in terms of materials, one of the key questions is whether for this technology of whether it's suitable for real life applications is, can you actually do this on curved geometries and complex geometries? So the idea is that we're going to be able to look at modeling those designs, and then hopefully trying them out on some curved geometries and seeing what we get. Do we have to consider altering the design, and then testing the accuracy as well, so we can combine all the mechanization of the processors with the modeling side of things and look at that. So yeah, it's a good question, and definitely something that is on our list.
So when you construct, this is something I was slightly confused about. When you do your spraying, are you spraying the pattern, or do you have a mask in place?
We've got a we're looking at different processes for producing those metasurface designs, but the idea is that you can continuously spray, and then you can create your pattern. So there's a number of options that we can consider.
So presumably you have a bit of sort of intense, you have a bit of thickness variation or some kind of degree of edge effect there. Yeah.
Well, this is one of the things that we've got quite a bit of know-how from the work we've done on lightning strike protection. So actually tailoring the coating process. Also being able to look at using the offline programming simulation to actually develop the actual coating process to either create thicker layers of coating or control the coating thickness over the entire surface, and then that's linked in with the methods for producing the metasurface. So you can either look at creating it via mask or looking at some kind of machining process, and then how applicable are those on complex geometries and at scale.
Lots of questions.
Yeah.
So lots of work to do. Great. We will watch this space. Okay. I will carry on down the epic list. A question for Ragip. What is the aspect ratio you can currently achieve with your nanofabrication tools? Are your light management metamaterials technologies applicable to all types of solar cells, e.g. silicon, SIGs, perovskites, etc.? I'm not a solar cell expert, so I will allow you to translate some of those.
Right, sure. So in terms of the aspect ratio, that for NIL we can get up to 4 aspect ratio of 4 for NIL, and for rolling mask lithography is an aspect ratio of 1. But we are expanding these capabilities to improve even further more the aspect. In terms of the applicability, I have summarized different techniques, 3 different techniques, and in the last one, which is the first one, which is the coatings, they can be applied on any type of solar module, and the nanoweb, the high efficiency transparent conductive films, that actually would work especially particularly for thin film perovskites, CIGS, which is flexible, and we can basically do MIG coatings on any sort of platforms as well. So in general, yeah, I would say yes. We have different type of coatings that are applicable to different type of platforms.
How durable are the coatings, Ragip? Because presumably this is then the outer layer of the solar cell, so it's being quite exposed.
Actually, for instance, the nanoweb, the metal coating, which I didn't describe in depth here, we would provide that film for perovskites, CIGS, as well as organic solar cell manufacturers, so that they can directly print their materials. So they can, instead of ITO, they can use this metal mesh as a more efficient platform. So that wouldn't be on the top. But the other coatings, which are these outer layer coatings, they would be basically applicable just to using adhesive, optically clear adhesive that can be implemented onto existing modules to improve the efficiency. Yeah.
So it can still have some protection on that top. Good. Okay. Right. Okay, this is a more general question, I think. So we'll have everybody's thoughts on this one. Do you see metamaterials having a significant impact on the future of the UK and global energy system? Do you see it being incremental, or do you foresee a big step change? So does anyone want to start with some thoughts on that one? I'm getting a no. Ragip, is yours? Oh no, Melissa's coming in. Fantastic.
I guess, you know, if you look at the work that we're doing and QinetiQ are doing, obviously that radar clutter is an issue. And if it wasn't an issue for the provision of wind turbines around the UK, then we wouldn't be looking at developing these technologies that are applicable at scale. So I think they are key to solving a current challenge for the UK. So yeah,
I'd agree. I think we are looking at them very much and with those thoughts in mind. And I think they do have wider applications. I think will there be a step change? It's difficult to judge because it's how quickly will industry actually take up solutions, and it's all around the cost-effective nature of it. I think it has the potential to do a step change and continued step changes, not just in energy but in other things as well. So but yeah, don't ask me too many questions about where, because there's quite a lot of fields where it could go into. But yeah, I definitely think from an energy perspective, you can just see by the work that us and TWI are doing that's the case.
Yeah, just to comment, there are different type of applications. Like for instance, for solar, it's more like an improvement since it's an existing technology. So I wouldn't say it's going to be a big step in that regard. But we are also working in alternative technologies like solar fuel cells, which actually have limitations because of the existing systems, and they do require, like for batteries as well as solar fuel cells, if you come up with a vertical solution which can enhance the systems in the system level, that using nanostructured or microstructured materials, that would be a big step change. And there are separate efforts that are ongoing, not only us, of course, in a global, like we can see there are different systems that are being developed. And hopefully we will see some big step changes as well, in addition to what we are working on towards with incremental improvements.
Movements all over the place, and both incremental and step changes. That's a very broad-ranging answer, as they tend to be for metamaterials in my experience. It sort of has capability in so many different areas, as you can see from the topics in this conference, that there is huge potential. Okay, Ragip, as we've got you, here is a question specifically for you. For the enhanced solar cells, how much additional cost do you anticipate for the module, and do your calculations indicate that the increased efficiency is worth the extra dollars per watt generated?
Yeah, that's a very good question, and that's exactly what we're aiming for. And currently, our anticipation is indeed we have actually less than, I mean, in terms of the efficiency enhancement, you would expect the solar cell module current cost is whatever we add is going to be basically, in terms of the cost, it's going to be less than the increased efficiency. So that will be basically enticing. Like it will be preferable coatings to validate that improvement.
Okay. Right, just looking down the rest of the questions because we've got only a little bit left in the session. Okay, so another general question about renewables, in that storage is a bigger challenge than capacity building. Now, nobody actually talked about storage really today, despite the title of our session, which was supposed to encompass storage as well. How can metamaterials support improved storage for renewables? I don't know if anyone has any thoughts on this question. I think it's possibly outside of the scope of the talks that we talked about.
I can say a few things here.
Yeah, that'd be great, Ragip.
In terms of the storage, actually, there are, as I mentioned earlier in one of the questions, we have hubs, I mean, in the UK, well, as well as US and other places for making like solar fuel cells, next generation solar fuel cell systems. And that's for more like basically storage system rather than just a conversion of the PV, right? And in that regard, there are several mechanisms that you can enhance this storage. For instance, you can have enhanced catalysis or enhanced light like trapping as well. So that could be still realized using metamaterial systems. I mean, well, maybe metamaterial is a very generic term. I mean, you can say nanostructured as well. But indeed, if you look at the literature, there are good examples, and we have actually current active programs that are working towards that as well. It's on the, I would say, more in a startup phase. However, it is a global effort. Metamaterials can indeed improve the storage part as well.
Okay, great. I agree. Okay, we will carry on to the next question. Now, this is an interesting question, and this is a question I had as well, actually. So that's very good to see. So the question is, would it be possible to use the lithographic print process, or I guess something like it, to create the radar absorption surface of a thin film that could then be put onto the wind turbine surfaces as sheets of film light transfers, rather than directly applying them or surface etching them directly? So this is a question, I think, for Melissa and Doug.
I guess it, from my perspective, it depends on what functionality you require, what proportion. It then comes down to the accuracy of placing those transfers, I would have thought. Given, for example, the experience of incorporating lightning strike protection systems into composite materials, dealing with expanded metal foil, and there's challenges with handling thin films and the accuracy of that placement. So I still think you would need some kind of mechanized placement process to allow you to accurately put those transfers where you need them to give the right response. But Doug may have further comment.
Yeah, so this is where I wish Greg had been here for the technical side. But I would say that anything that requires accurate placement over, because it's such large scale. So at the moment, you know, the manufacturing process doesn't use robotic placements or anything because they're just so big. So actually, if it requires really accurate placement, you know, to achieving that by hand is a challenge. I could say that. In terms of the other side, I'll annoy my technical expertise when he comes back in and see if I can get a more detailed answer.
Yes, do you pass all these questions on to your colleague as he's left you to deal with?
These are all good questions that you know, when you're thinking about technologies, is, you know, what are the practical implications of upscaling these, and what works for one application may not work for another, or there's ways and means of mechanizing things, but there may be an alternative way of mechanizing a process that's better suited to something like a turbine blade over something that's a smaller but maybe more complex geometry, for example.
Yeah, I think that's right. I think it gets forgotten sometimes, doesn't it? The sheer complexity of these manufacturing processes, and it varies so much. Really, what you need is a big toolbox that you can use.
And then ultimately, it's got to be cost effective. So it depends on what the technical need for the technology is versus what everybody's prepared to pay to implement it, and those costs at the initiation stage versus once you're into mass established production techniques.
Yeah, because at the moment, presumably both of your projects are essentially looking at sort of taking an existing blade and applying your technology to it. It's not integrated into making the blade, which is what you'd hope for eventually. Yeah,
so I know there's a slight difference to ours. We integrated in because it's structural. Okay. We actually use the RAM itself to form part of the structure. So I mean, it's a pick and choose. So arguably, if you just lay something on top, you don't have to mess with the structure. If it adds too much weight, that's a challenge. But it also, you know, arguably wouldn't interact too much. Whereas it was with ours, because it's structurally, you have to look at the design of the structure itself and integrate it into that design of the turbine blade itself. So they are slightly different approaches. But yeah.
both very valuable. And I think if you're
Oh, yeah.
thinking about potentially retrofitting, you know, you then can't do that with your process. But if you're starting from scratch, perhaps you used a different process, and away you go. Great. The next question I think I can probably answer: are the TWI and QinetiQ work on wind turbine coatings collaborative or parallel technologies? They are parallel technologies, I would say, and not collaborative. It just so happens that we have both of you here talking about complementary areas. I think that's right. Tell me if I'm wrong.
Oh, that's right.
That's right. Good. Great. Okay. So we have a couple more questions, which is good because we are almost at the end of our session. We have had so many questions. A question from Bernard Watts. If metamaterial is low dimensional nanoscale, is chemical stability a problem, particularly when it is a multi-phase or when there is a metastable phase present? I think this is possibly mostly generated from Ragip's talk, because that was where we were more on the nanoscale patterning. So I don't know if you wanted to give us your thoughts, Ragip, on chemical stability.
Yeah, sure. Actually, our current, we have different technologies, and like, for instance, for relating to the features that I described on the like coatings, they are currently implemented in banknotes. Like we create security features on banknotes, and they have very rigorous requirements for environmental stability and chemical stability, and we do have additional coatings on them to realize that. And different as a different material system, which is, let's say, for instance, nanoweb, which is a metallic film, that would actually also have some kind of, that would need a coating actually. I mean, unless you use that encapsulate it within the solar module itself, which is the case for solar cells. But for other applications, we do need some kind of additional encapsulation to protect it from environmental, and that's being done as well for different applications.
Yeah, because I suspect it's probably the same in the wind turbines. I know, Melissa, I think you talked about doing environmental testing, didn't you, on your samples, and that's a neat thing to do. That's the sort of last question in it as well that we've got, is about how do the coatings stand up to environmental conditions?
Yeah, these are some of the things that we're doing as part of phase 2 project, looking at, you know, and we've got a lot of experience at TWI about looking at coatings in offshore environments from, you know, several years worth of R&D looking at oil and gas platforms and also wind turbine applications. So we're very well engaged with testing in these kind of environments, and linking in with Warwick. Obviously they've got knowledge of specific testing and the capability to do tests that are important in the context of blade technologies as well. So that's the beauty of these, you know, the project, that we're able to bring together relevant expertise to address all these challenges, because ultimately for something to go into service, you need to have been able to validate the coating systems, and actually then think about how that gets incorporated into standards and things longer term as well, for manufacturing specifications, etc.
Yes, which obviously has an impact on our earlier thoughts about how can we have a step change in something, because so many of these things have to jump through so many hurdles before they can actually make that step change, that it may feel a lot more gradual than it really is.
But I think this is one of the benefits, you know, the experience we've had at TWI, the knowledge and expertise that we gain in one area is applicable to other applications. We can bring that to the party. So
yeah, absolutely, totally. Fantastic. Did anyone have any further thoughts to add on environmental conditions as we bring it to a close? Okay, well, that is all of our questions, and we are just about at the end of our session. So I'm going to wrap things up just there. I would like to say a big thank you to our fantastic speakers. It's really fascinating talks. And thank you for sharing so much of your information and thoughts in the Q&A as well. I think it's been a really lively, and for me, a really informative Q&A. I think I had a good perspective into the other side of the table to some extent. When I'm thinking about pottering around in the lab and making something small, I really need to be thinking, how do we make this big, and how do we get it out there on a wind turbine? That's my new goal, get something big enough that it can go on a wind turbine. So thank you very much, Doug, Melissa and Ragip, and thank you to our behind the scenes people who have been seamlessly managing things for us here on Zoom. And the final session of the conference is everyone back together for a Q&A panel discussion. I believe that starts at 4:30, so we've got a little bit of time for break before we get that final session. Thank you all very much for coming to this, and hopefully see you in another session very soon.
Thank you.
Claire.
Thank you.